So in this video, I'm going to remind you of the stuff that you're supposed to learn last year, hopefully you did. We'll talk about Eulerian paths, Eulerian circuits, and Hamiltonian circuits. First of all, what is the difference between a path and a circuit? So if I've got this graph. Okay? Now, a circuit is like what we think a circuit is. It's basically if you're going around, you start at a certain point, okay, let's say you start at A, went to B, C, D, E, F, back to A. If you start at one vertex, you went through a whole bunch of vertices, you came back to where you started, that's a circuit. Okay? Path is where you went from A to B to C to D to E to F. You didn't go back to where you got to. Okay? So that's a path. Okay? Path and a circuit. Now, what is an Eulerian path? Well, Eulerian, let's start with Eulerian. Let's start with Hamiltonian. Okay? So Hamiltonian circuits are basically circuit where you went through each one of the vertices. Went through each one of the vertices once, and you got to where you started. So if I'm going from A, okay, I'll do it here, from A to B, to C, to D, to E, to F, back to A, that's a Hamiltonian circuit. Okay? And some graphs will have Hamiltonian circuit, some graph will not have Hamiltonian circuit. An example where you won't have a Hamiltonian circuit, think of something like that. Okay. So let's say I have A, B, C, D. Okay. I can go from A to B to C to D. If I want to go to A, I have to go through B. So then it's the second time that I've gone through the vertex, so it's not going to be Hamiltonian circuit. If I could add one more vertex, okay, that will work, because now I'm going to go from A to B to C to D, back to A, okay, and I didn't have to go through any other vertex. Okay, so some graphs have Hamiltonian circuits and some do not. Okay, how do you know if a Hamiltonian has graph has Hamiltonian circuit? Well, there's a couple of tests that you can find out. One is Dirac and one is All. You are supposed to do in grade 10. Yeah, I'm not going to get into this here. Maybe later on, and if not in this year, we'll come back to it in grade 12. But I don't think we need it for our job here, so we'll just leave it. Right. So if this is Hamiltonian circuit, what is what is Euler about? Okay. If Hamilton is all about the vertices, I have to visit all the vertices. Euler sound like edges, E for edges. Euler is all about the edges. Okay? So, Eulerian, let's start with Eulerian circuit. So, Eulerian circuit is a circuit, so I start and end in the same vertex. But it's not about visiting each vertex once, it's about going through each edge just once. Once and once only. So let's have a look at this one. So we'll start from A, we'll go to B, I'm going to turn it into blue so you can see if it's blue now, that means we use it. Okay? Then I'm going to go to C, then I'm going to go to D, then I'm going to go to E, then I'm going to go to F. Now I can go back to D. There's no problem of revisiting a vertex because Eulerian circuits are not about visiting each vertex once. It's about going through each edge once. So I went back to D. I'm going to go back to D. Again, I can visit a vertex more than once. I'm not allowed to visit an edge twice. Going back to F. Going back to A. So that was an Eulerian circuit. Okay? A to B. I'll write it down. Okay, so we went A. I'm going to write it down. I'm just going to show you again. So A to B, to C, to D, to I'm doing a different one now. There's more than one option. Yeah? To F, to D, to B, to F, and to A. So this graph has an Eulerian circuit. We're going to pause here for a second. Okay, so going back to our original graph, what I'm going to do now, we saw that this graph has an Eulerian circuit. Okay? Now what I'm going to do now, I'm going to get rid of this edge. Get rid of this edge. Now, there is a theorem that again you learned last year, that to have an Eulerian circuit, each degree must be even. Okay, so maybe I'll just put that back in here. Right? The degree of this is 2. Here is 4. Here is 2. 4. 4 and 2. If all your degrees are even, okay, you will have an Eulerian circuit. If you think about it, if it's even, that means that for every road path going in, there's always a path going out. So I'm never going to get stuck in that vertex. Okay? However, if I take this edge now the degree here is going to be 3 and the degree here is going to be 3. In this case, that means we are not going to have an Eulerian circuit. Because if I go to B, imagine I'm going to B, I get out of B, I come back to B, and now I'm stuck. I can't go out again. If I want to go out, I have to reuse the same edge. And that means it's not an Eulerian, because I'm not allowed to repeat the edge. I can go back to the same vertex, I'm not allowed to go on the same edge twice. So if I have some odd degrees, I can't have Eulerian circuit. However, I can have an Eulerian path. Okay? What is an Eulerian path? Eulerian path is, again, a group of edges, a sequence of edges going through the road, not repeating any edge, going through all the edge, but it's not a circuit. It's a path. Meaning I start at one point and end at another point. Okay? So let's start from D. Okay? If I'm going from, let's say, B, okay, I'm going to go to C, to D, to E, to F, to D, to B, back to B. I can't go back to B as long as I don't go on the same edge. To A, and then I go to F. So I started, if you remember, I started at B and I ended up at F. I went to B, I went to C, and so on, so on, so on, so on, and I ended up eventually at F. So it's certainly not a circuit, because I didn't start and end in the same place, but it is still Eulerian. It's an Eulerian path. I went from one point, went through all the edges, ended up at this different point, different vertex, but I covered all the edges once and only once. Eulerian path. The rule or the principle, the theory that you learned last year is that if you have all the degrees even, 2, 4, 2, 2, except for two vertices where the degrees are odd, then you can have an Eulerian path. You can't have an Eulerian circuit, but you can have an Eulerian path. I'll just recap this whole thing, okay? So, for Eulerian path and circuit, if you, the criteria, the only way to have an Eulerian circuit is that all degrees are even. If 2 degrees are odd, then you can have an Eulerian path and not an Eulerian circuit. If there's more than 2 vertices with odd degrees, then you can't even have Eulerian path. Okay, hopefully that makes sense. I'll just pause here and we'll do a few examples. Okay, so now I'm going to just do a couple of examples from exercise 1.1. Okay, so they give you a few graphs. I'll just do 2 of them. I'm doing quite a lot of examples here. And they're asking us to find out the Eulerian path or circuit. So if there's a circuit, do a circuit. If you do a path, then do a path. And a Hamiltonian circuit, if it's possible. Let's start with Hamiltonian. Now, when all these vertices are here, okay, very easy to create a Hamiltonian circuit. What is a Hamiltonian circuit? I don't have to work. Hamiltonian is all about, one of the books I saw, Hamiltonian is all about hotels. So imagine all these vertices are like hotels. I need to go through all the hotels once and once only. Don't worry about the roads between the hotels, it's about the hotels. So Hamiltonian circuit, for example, could be A to B to C to D to E to F. Back to A. I don't have to do these edges. It's not about edges. Hamiltonian is about hotels, about vertices. Okay? So definitely have a Hamiltonian. Okay? A, B, C, D, E, F, A. What about Eulerian Circuit? So let's have a look at the degrees. I've got 4, 2, 2. I've got a 3 here. I've got a 3 and a 2. So I've got 2 vertices that are odd degrees. Therefore, I definitely can't do Eulerian circuit, but I can do Eulerian path. What is Euler? What is Euler about? It's about edges. Euler edges. Okay. So basically, I need to cover all the edges once and once only. I can't repeat an edge. Okay. So because I have 2 odd ones, I'm not going to be able to do Eulerian circuit. But because it's only 2 and not more, then I can do an Eulerian path. Now the trick here, the easiest way of doing it is if you start and end in the 2 odd ones. So I just do it. I don't know if it's easy. I don't know, for some reason I find it easier. Okay? I always start and end in the odd degree one. So I'm going to start from here and I'm just going to squiggle it. Okay? So I'm going to go to F, to A. I can just go to B, to C, to D. Okay? I can go back to A. I can revisit the vertex. It's not a problem. I just can't go through the same edge ones all at once. Back to E, and I end up at D. So I went from E to F to A to B to C to D to A to E to D. I didn't start and end the same point, so it's a path. It's an Eulerian path. Right, let's look at the bottom here. Ooh, that's a little bit of a nightmare. Eulerian. Let's start by looking at, I'm just going to pause here for a second. Okay, so if I'm looking at this graph, okay, let's look at the Eulerian first. Okay, so do I have any odd degrees? Okay, I've got 3 here, I've got a 3 there, I've got a 3 there, and 3 here. So I've got more than 2 vertices with odd degrees. So I definitely can't do an Eulerian circuit and not even Eulerian path. So no Eulerian. Now Hamiltonian. Unfortunately with Hamiltonian there's no different way. There's no test that I can do to find out whether I can do a Hamiltonian circuit or I can't. It doesn't work like with Euler. Okay? Like I said, there are a couple of tests that if the graph fulfills them, I can definitely do a Hamiltonian circuit. But you might even find a Hamiltonian circuit if it doesn't pass through the test. It's not really an issue now, so I'm not going to bother about it. But it's just about trial and error. Just trying. Can I go through all the vertices, okay? Through all the vertices, but without repeating more than a vertex more than once? And you can have a go at it. There's just no way. There's no way I can do it. Just look at this. If I go from A, B to C to D, and I can go whatever, all these ones. Did A, B, C, D, I carried on. I still haven't done M. Okay, so I've done A, B, C, D, E. I need to get to M. Now, how am I going to get to M? Well, I have to go either through A or through C. So I'm going to have to repeat the vertex, and therefore it's no Hamiltonian. So there's no Hamiltonian, no Eulerian, nothing. Okay, let's see if there's another example I need to do here. Okay, the next example, they're asking me, discounting isomorphic graphs. In other words, don't consider isomorphic graph. How many connected simple graphs can be drawn on 4 vertices? Okay, so I've got 4 vertices. I'm looking for how many graphs can I do that are both simple and connected. Connected means that I can get from each vertex to another vertex in some way. So let's say this is not a connected one because I won't be able to get to that vertex. But this is connected. Okay? What does simple mean? Simple graph means that there's no loops and there's no repeated, what do we call it? multiple edges. Okay, so I'm looking at simple graph. So for example, this is one. Okay, that is one graph. Now what did they tell us about not considering isomorphic graphs? If I have this graph, okay, it looks different, but they are isomorphic. They're the same graph, isn't it? I mean, what is that? It's just basically taking this, moving it to there. Remember, isomorphic graphs are graphs that I can move the vertices around, move the edges around, but I can't cut edges, I can't add edges, can't obviously add or take away vertices. So that's just one, okay. Now what about, let's just try and think about others, okay. So I can do another one which is like this, okay. So that is obviously simple and connected, okay. I can do that. That's another graph which is connected and simple, okay? And I can even do that, okay? Remember, that's what we call complete graph. So all the vertices are connected to all of them, to all the other vertices. This one, if you remember, we call regular graphs, okay? We have the same number of, the degrees are all the same. Each vertex is connected to the same number of other vertices. Okay? What about that? Does that qualify? It's definitely simple, but is it connected? No, it's not connected. I can't go from here to there. There is no way. From here, I can't go to there. I just go to this edge. But this is not connected. So as far as I can see, I can find 4 graphs. Can you find another graph? I don't know, let me just think about it. No, I can't find of anything else. I mean, obviously, you can take, let's say, these 2 points, these 4 points, stretch them up and just make one line like that. That looks different, but really is the same. It's isomorphic. All I did is just shifted these 2 points. I didn't cut any edges. Okay, so as far as I can think, I can only think about 4. But have a go at it. If you find more, just let me know. Okay? I just want to do one last thing to finish this video. Just to finish up now, let's recap this Eulerian Hamiltonian. Hamiltonian is about, or Hamiltonian circuit is a circuit, I start and end the same vertex, that visits every vertex once and once only. I'm not repeating the vertices. Okay? Eulerian is a path or circuit where I go through each edge once and once only. Okay? Eulerian is about edges. Okay? Now, if I have a graph where every vertex has an even degree, I will be able to find a Eulerian circuit. If there are some odd degrees, then you won't be able to find Eulerian circuit. But if there are only 2 odd degree vertices, you should be able to find Eulerian path, okay? Which means you start and end in a different vertex, but you cover every edge once and once only, okay? That's how you can definitely tell if there is Eulerian circuit path or not, none of those. For Hamiltonian, unfortunately, we don't have these rules, okay? We've got some rules that will allow, if they pass these rules, then there definitely is a Hamiltonian circuit, but you might even have a Hamiltonian circuit without passing these rules. So I'm not going to get into that now. It's not really that clear. My advice to you, or what you need to do is just try. Just try and find Hamiltonian circuit. And if you can't find it, then probably there isn't. Okay. You can do exercise 1. Have a lovely, lovely day.